Okay, once again, welcome back to my YouTube channel. Now, this is Santos Capillan Jr. wishing you a good day. Now, actually, what I'm going to do today is uh, I just finished my frequently asked question in building management system. Now, I feel more energetic, so I want to create another video tutorial to complete or to show you the almost complete control logic program for our twin exhaust fan control. Okay. Now in this video tutorial, I'm going to show you the control logic for this equipment. Okay. So let me walk you through with my logic program. Okay. Now, as you can see here, I have put some comments. Okay. Now, this portion, okay, so this is my EF1 run hours totalizer, okay. So this portion will generate the run hours accumulation of exhaust fan number one, okay. Then at the same time, it will run the maintenance alarm, okay. So uh, the maintenance alarm will be raised by our control logic to inform or to notify the BMS operator that it's time for the operator to notify the maintenance personnel to do some maintenance or preventive maintenance for the said equipment. Now, this preventive maintenance schedule are being prepared by the facility management. Okay, so based on the inputs of the maintenance engineer, then he can give you the run hour set point. Okay, this my I have a block here. This parameter value real. Now my initial value is only 5 because this will be used for testing the logic. Now, basically, if it's this system is online, so the run hour set point may be around 500 hours. It will always depend on the uh, maintenance engineer. Maybe he will give you, okay, 1,000 hours. Once the equipment reach 1,000 hours, then that's the only time to raise the maintenance alarm. Now, this set point will be flexible, meaning the BMS operator can adjust this based on the requirement, okay, actual requirement. Now, this I'm using here the runtime or RT block, okay, runtime totalizer, okay. So this one, I already discussed this last tutorial, I guess, but let me tell you again. Now, runtime totalizer is the one recording the run hours of the equipment. Now, there are two inputs, then one output. One input is the run status, okay, run status of the equipment. Or maybe if you want, you can also use the airflow status of the fan. So you can create an end block or block rather. So you will check the run and the airflow status. So any one of the two inputs, let's say you run status becomes 1, then this totalizer will start counting. Or if the airflow is 1, then this air runtime accumulator will starts to count also. Okay, so because sometimes your equipment is running in manual mode. Okay, so maybe someone is just running it for in manual operation, is trying to observe something, so that running hour should be also recorded. Okay, so here you will be using one runtime block. Okay, then here this one, the input will be coming from run EF1 run status or airflow status. Then this PVB, this is parameter value binary. Okay, now initially it is 0. Now if in your BMS graphics you set it to 1, then it will reset the runtime accumulated. It will go back to 0. Okay, now I discussed already that in the run hour, now the unit or the parameters you can set it to 0. for hours, 1 for minutes, and 2 for seconds. Okay. Now we set it to minute for the sake of testing the logic. Okay. So because later on you might simulate your control, so you want to make it 0. You make it the unit for this runtime, you will make it to 1 so that you will not wait 1 hour before you will see any change in your control logic. Okay. So as an advice, you can set it to 1 per minute. Then you can set also the set point for shorter period. So you will not wait too long just to see what is the response of your logic to the condition. Okay, so this is for run hour totalizer. Okay, the same approach for EF2 run hours. Okay, so I don't need to explain it. Now here EF1 airflow alarm logic. Okay, now airflow alarm, this is the condition where, let's say, the BMS control logic or the BMS starts the fan. Okay, as I said, BMS is taking the control of the equipment when the equipment selector switch is in automatic. Okay, so based on your sequence of operation, your control logic program will start the fan. Now, let's say your BMS started the fan. Okay, then after some time delay, okay, you did not receive the airflow, then that's the time to raise airflow alarm or EF1 run fail. Okay, so as you can see here, I have here one binary output block. Then this one will be the one to generate the EF1 run fail alarm. So meaning our control logic program started the fan. Okay, let's say your motor control already the contactor is energized, then there's some problem with your fan. Let's say the fan is belt driven, maybe the belt is loose or the belt is broken. Even the motor is running, but the fan being driven is not working because of maybe the belt is broken. So the fan will not rotate and it will not deliver air. So there is no airflow. So this is the time that BMS is running run fail alarm for that exhaust fan. Okay, so again, the BMS operator will be notified. Okay, I have run fail alarm in my EF1. Then he will inform the maintenance people, kindly check the equipment. Maybe there's a problem with the belt, if the fan is belt driven or some other issue in the motor control. Okay, so this is how you are going to define your logic for airflow alarm. So what are the blocks I used here? I used a BO block, okay. Then I use this one, SR block, okay. So this is set, reset. It's like a flip-flop, okay. So set, reset, okay. So the inputs are S and R. So the one that will reset is the EF1 alarm reset. Okay, now let me explain this public again, once again. Now the public, okay, you can set it to public when you say public because during binding of your BMS graphics, okay, you will not find these points in the system if it is not in public or if the checkbox is not checked. Okay, so it will not appear during binding. So that if you think you will be needing these points in your control logic during the binding time of your BMS graphics, you have to make it public. So you have to make it public so it will appear during the binding time of the BMS graphics. Okay, I have shown you already how to bind BMS graphics to physical points and software points. Okay, so just bear in mind that this public is very important. Okay, I will show you like this one. Okay, like this end gate. So it is not public because you don't need this during binding time. Okay, so if you need the black during binding time, that's the time you have to make it public. Okay, now I have here a delay block. As you can see here, I did not make it public because I don't need it during binding time. Okay, so only those important points that I need to display in my BMS graphics, I have to make it public, or those points that I have to change the values, I have to make it public, okay? Because the one that will be dealing with the BMS system after handing over the project is the BMS operator. BMS engineer will not sit in front of the BMS workstation. You need only there a BMS operator. So you must make your control logic program flexible that the operator can do some changes in the equipment parameters. Okay, they don't need to call the BMS engineer. Okay, change the set point. They will not call the BMS engineer, change the parameter. This one, I don't want in the sequencing. I don't want 168 hours. I want double time. Okay, so you have, as a BMS engineer, you have to make your program flexible so that you will not be needed during operation. Okay, so that is my airflow alarm. The same logic also going to the EF2 airflow alarm logic. Okay, now here, this is my EF1, EF2 start stop logic. Okay, so this logic, okay, this one will be the one to start and stop the exhaust fan based on the sequence of operation. Okay, now here, this is my EF1 changeover or sequencing. Now this changeover sequencing handle the changeover of exhaust fan 1 and 2. Now when you say changeover, let's say during startup, okay, initial condition or initial startup, now exhaust fan will run, exhaust fan number 1 will run, okay? Then after some time, let's say you specify here in the sequencing, you will specify that every 168 hours, my exhaust fan will change over. So meaning EF1 started in the initial, in the startup, then after 168 hours, then it will stop, then EF2 will run. Then after EF2 runs at 168 hours, then it will stop, then EF1 will run. Now, this changeover is a good engineering practice to implement equal wear and tear for both equipment. So it is not a good practice that EF1 will just run continuously, then EF2 will just kick in if something happens to your EF1. Let's say if it trips, that's the only time that EF2 will run. Okay, so that is not a good practice. So that's why in our control logic, we are introducing changeover or sequencing. So to handle the sequencing, we are using this portion. Okay, so we are using the same blocks, the runtime totalizer, then we are checking the accumulated time, set point for sequencing, let's say every 1 week, 168 hours. Then if it reaches, then it will set this flip-flop or SR block. Then it will change over from EF1 to EF2, EF2 to EF1, EF2. Then the tripping also will be handled by this start and stop logic. Okay. So what are the other blocks that I introduce here? Okay, now I introduce here this expression block. So what is this expression block? Now, as you can see here, my expression block, I did not put an identifier because I will not be needing this during binding of my graphics, BMS graphics. So I did not make it public and I did not put any identifier. Okay, so I'm just using it for my control. Okay, now the expression block, you can specify binary, integer, or real. Now I'm using binary, meaning the output of this expression block will be binary. Okay, it will be 0 or 1. Okay, now because you can have also expression block that will give you an integer output, then a real output. Okay, so this time I'm using only an expression block integer binary output. Okay, now what is my condition? A, so I have 3 inputs in this by expression block, A, B, C. So what is the condition? A, if A and B and C, meaning if A is true, and B is true and C is true, then the output should be 1. Okay, so it's just like combination of several AND gates, or several AND gates and OR gates, or several AND gates, OR gates, and NOT gate. Okay, so if you don't want to use expression block, you can use combination of AND, or not. Okay, but for me, I think it's more convenient if you will use also expression block, because it will shorten your control logic, because maybe your control logic, you have so many AND gates and OR gates combined together. Now you can eliminate this AND and OR gates and NOT gate combination by just using an expression block. Okay, so here I've used implement here expression block. Okay, then delay block, SR block. Okay, then later on I will be trying to simulate this to show you how it works, but it is better to simulate this during online testing. Now I hope I can do the online testing in the month of March. Okay, because I have to prepare the demo board. I already show you my demo board. I have to prepare it, and I have to prepare my front-end computer, and I have to prepare that demo board. So hopefully I can start doing the online checking of this control logic program in the month of March. Okay, so hopefully everybody, or I mean my subscriber, will bear with me. Okay, because I have so many video tutorials that I have to prepare. This is only exhaust fan. I have to show you an air handling unit, how to control an air handling unit. Okay, I have to show you how to control submersible pumps. I have to show you how to control chilled water system. I have to show you how to control booster pumps, and so on. Okay, so bear with me. In the month of February, I will be doing all this offline checking or offline configuration. Then in the month of March, I hope I can start the online configuration. Okay, now I think this is enough for today. I have shown you now the almost complete logic control of the twin exhaust fan equipment. Okay, so I have here, to wrap it up, I have the airflow alarm logic generation. So these are the software points. Then I have the runtime totalizer, again software points. Then I have my EF1 start stop logic. Okay, how I am going to start and stop EF1 and EF2, and how I'm going to do the sequencing, okay, by using this flip-flop blocks or SR block combination with and or and NOT gates, and using some expression blocks. Okay, now as I said, if your control logic is becoming complicated, you can break it down to smaller, manageable control logic program. Let's say you will just write one small program for EF1 start stop. Then you will write the program. Okay, so you can write one program for EF1 start, EF1, EF2 start stop and sequencing. Then you can write one small program for runtime totalizing of EF1 and EF2. Then another small program for generating all the alarms. Okay, so you will have three small programs that are easy to understand because it is small and manageable. But if you have a big logic, sometimes you feel you cannot follow the logic. So it's an good advice to break your big and complicated control logic into smaller uh, control logic program which are manageable. Okay, now hopefully I have given you an idea how are you going to prepare a control logic program using functional block programming, and later on actually I've shown you already one script programming. Now maybe we can write, or you can write the equivalent script program uh, for this FB or functional block programming. So again, once again, thank you very much for watching my video tutorial. And if you are new to my channel, please don't forget to subscribe and click the notification bell so you will be always notified if a new tutorial is available in my channel. And thank you, and I hope you will watch all the video, especially for the new aspiring BMS engineer, so that you will grasp all the concept and ideas involved in building management system. Thank you very much, and God bless us all. And Santos Capillan Jr. saying bye for now.